Section 11.4, Calculus in Polar Coordinates. So we learned we can convert polar to rectangular. And so just a little bit of review. If we have r as a function f of theta, then we have an equation for x. It's r cos theta, or f of theta cos theta. And y becomes r sine theta, which is f of theta sine theta. Now, basically, we've converted a polar to parametric. And so all the things we learned about parametrics would apply to this form after we convert polar into parametric. So we can find the derivative of x using the product rule. So you leave the first alone, take the derivative of the second. And then you take the derivative of the first and leave the second alone. And we do the same thing for dy d theta. And so now we can find the slope of a tangent line for polar coordinates because we did this with parametric. In parametric, to find dy dx, we took dy d theta dx d theta and divided that. And it's actually dt, but it's just a variable, so it doesn't matter. So we found dy d theta right here and dx d theta here, so you just plug that in. So in essence, we are doing the slope of the tangent line for the polar in parametric form, where we can find x and y by doing r cos and r sine theta. And so really we haven't done anything new for finding slope of the tangent line for polar coordinates. It's just parametric that we've converted. So example 1, find the slopes of the tangent line to the curve r equals 10. So first we have to find x, which is r cos theta, which is 10 cos theta, because 10 is our r. And similarly, we do y is 10 sine theta. So we're going to find dx d theta. It's going to be minus 10 sine theta. And dy d theta is going to be 10 cosine theta. So the slope of the line, dy dx, will be dy d theta over dx d theta, which will be 10 cos theta over negative 10 sine theta. And things start to cancel. So we get negative cotangent theta is how we're going to find the slopes of the tangent lines for the curve given. All right, so that was a pretty straightforward one, not too hard. Now this one's going to be a little trickier, the next one. All right, so to be vertical, the slope would have to be infinite. To be horizontal, the slope would have to be 0. So we're going to change this to x and y coordinates first. So we're going to have x equals, it's going to be r cos theta. So it's going to be 1 minus cos theta, and y is going to be r sine theta. So we have to find dx dt, or d theta. We're going to use product rule. So leave the first alone, take the derivative of the second, plus take the derivative of the first. Derivative of 1 is 0, derivative of cosine is minus sine, but that minus and minus becomes sine, and we're going to leave the second alone. Now we're going to find derivative of y, so we're going to leave the first alone and take the derivative of the second, and we're going to take the derivative of the first and leave the second alone. All right, so now dy dx will be the top one. And this will be sine squared over the bottom, which is dx dt, which will be 1 minus cos theta minus sine theta plus sine theta cosine theta. Okay, we're good here. So this is dy dx. In order for this to be horizontal, tangent line, dy dx would have to be 0. For that to happen, the numerator would have to be 0. So I'm going to set the numerator equal to 0. Well, how am I going to set that numerator equal to 0? Can I factor that? I think I can. Let's look at this. So let me rewrite this. Distribute the cosine. So it's going to be cos theta minus cos squared theta plus sine squared theta equals 0. Well, here's my thought. I'm going to rewrite sine squared as 1 minus cosine squared. We learned that in trig. But that will give me everything in terms of cosines, which is much nicer. So I have minus cosine squared, that's minus 2 cosine squared theta, plus cosine theta plus 1. And I believe that's right. So I have a cosine theta and plus 1. So I'm going to try factoring this. Before I do that, I'm going to multiply both sides by negative 1. I don't like my first term to be negative, so I like that better. And then factor this, I'm going to do 2. Okay, let me give me some room. 2 cos theta and cos theta. These have to be 1. That's 1 cos, that's 2 cos. To get negative 1, I need negative and positive. And so that's what I have. I set each of those equal to 0. 2 cos theta plus 1 equals 0. Cos theta equals 1. So I just added that 1 over there. So here we get cos theta equals negative 1/2. Well, what angles have a negative 1/2? And look at my domain. I was given a domain on this from negative pi to pi. So negative pi to pi. So what angles? That's going to be negative 2 pi over 3 and 2 pi over 3. And when will the cosine be 1? It's just going to be 1 at 0. And that's in my domain. So those are my 3 angles. So that's going to get me horizontal tangent lines. Okay? And then I need room for my vertical tangent lines. So I'm going to erase this stuff. And this time will be vertical tangent lines. So vertical tangent lines will occur when the denominator is 0, because that will give me infinite slope. So I'm going to set the denominator equal to 0. Well, the first thing I noticed, they both have a sign. So let me take that out. I'm left with 1 minus cosine theta times negative 1 plus cosine theta. I'm going to distribute, well, I'm going to set this equal to 0. I'm going to distribute this negative to both these. I'm going to get cosine theta minus 1 plus cosine theta. I get sine theta is 2 cos theta minus 1 equals 0. So I set each of these equal to 0. When does the sine theta equal 0? That's going to be at 0, pi, and negative pi. And that's my domain, so those work. I add 1 to both sides, divide both sides by 2. And what angles has a cosine of 1/2? That's going to be pi over 3 and negative pi over 3. So those are the angles that will get me a vertical tangent line. So one thing I'd have to watch out for is when the denominator is 0 and the numerator is 0, then I have a different situation. I no longer have a vertical tangent line. So we had one angle where that occurred. That's going to be 0. So what I'd have to do, and I'm not going to do it here, I'd have to find out what happens as theta approaches 0. So I'd have to take the limit of this function as theta approaches 0, but the top approaches 0 and the bottom approaches 0. So it looks like L'Hopital's might be the way to go. And if you do that, you end up with 0. So 0 ends up being a horizontal asymptote situation, not a vertical asymptote. So now, how do you find areas in polar graphs? Before we do this, once upon a time, when you had, probably in geometry, but more so in, I know we did this in pre-calculus, the area of a sector. So if you have a circle and it has a radius r, so let me label that, and you have part of that circle, theta. So you have theta. Well, they want the length of this piece here. That's called arc length, and that just equals r theta. Okay? But that's not what we want. We want the area. The area comes out to be 1/2 r squared theta. So that's going to be important in what we're going to do next. So what's weird about polar graphs, finding areas, the way that they're formed, if you remember, you're going to plot a bunch of points. And you're going to create a curve that way. So it's created by angles. Angles form these. So what happens from this angle, let me change the color of that. We'll go golden. So if I go from that angle there to that angle there, that produces this little strip here. But I can approximate the area. I'll call that A1. That area, A1, is going to be 1/2 r squared delta theta. Whatever that angle is, that's going to be an approximation, because this works if you have a circular arc. Now, obviously, that's not a circle, so it's not quite accurate. Now, if we did another one and call that A2, we would have 1/2 r squared and delta theta 2. And so on and so forth. If you kept doing this all the way till you get to your last one, which we'll call A sub n, if you add those up, those will give you an approximate area of that curve. But we can add those up, and we add it up using a process called integration. And we start at our angle theta, we end at beta, and we're going to add up. Now remember, as the number of these little sectors goes to infinity, then the error becomes 0. And when it goes to infinity, our delta theta becomes d theta. So it just becomes 1/2 r, which is r of theta squared, d theta. And that's how you find the area of a polar graph. But the important part to realize, it's formed by a starting angle and an ending angle, and as you sweep across those angles, so starting angle to an ending angle, and basically you're getting your areas by a lot of strips going out at an angle. That's very important to understand how you're getting those areas. It starts at an angle, ends at an angle, and you just sweep your way across. So we have this definition, area of the polar coordinates, and it's this formula. But again, make sure you understand what alpha and beta represent and how this works, or else you'll get confused on finding areas. In this next example, we want the area of the green shaded region, just that part. Well, how am I going to do this? Well, I can find the area of this red region. Now the problem with that, I have too much, because that green, that covers the green, but it has extra stuff. But the area of the red, it's going to be the integral from alpha to beta, and it's going to be 1/2 r squared. The radius is g of theta, d theta. Now the problem is, it's too much stuff. I need to get rid of this blue area here. So I need to subtract the blue, which is the region inside of f of theta. So again, the area of that is integral from alpha to beta of f of theta squared d theta. So that is the area of the shaded region right there. If you want, you can combine these. They have the same limits. So we can do that, but then we can do g of theta squared minus f of theta squared d theta. And so that will be as a combined, but I would just recommend keeping them separate so it makes more sense, so you don't run into any issues. But that's example 3. We can keep going here. Example 4. Find the area of the 4-leaf rows r equals f of theta, which is 2 cosine 2 theta. Now here's where we need to make some connections. So I have graphed the function both in a polar graph and in a Cartesian coordinates. So what point does that represent? That's an angle of 0 and an r of 2. Angle of 0, r of 2. So that will be that point. Now I need to find where it crosses right there. What crossing point is that? You can actually find that by hand. If this were a calculator, you graph it on a calculator and find the intersection point. But you can do that by hand. You want to know when that equals 0? Well, that means divide both sides by 2. Cosine of 2 theta will still be 0. And you ask yourself, what angle is a cosine 0? And the first time that happens is pi over 2. Divide both sides by 2, we get pi over 4. So now we know this point here is pi over 4. So graphically, looking at this, here's pi over 4. So as I go from 0 to pi over 4, the r gets smaller and smaller and back to 0. So it's going to be that portion there. All right, next, as I continue, I need to find the next crossing point right here. But we can do that. When is the next time a cosine 0 after pi over 2? It's 3 pi over 2. If you divide by 2, it's going to be 3 pi over 4. So that next point there is 3 pi over 4. So I'm going to draw that out here. I'll do it in blue. I never colored the first one. This is red. This is blue. And so where's that located on our graph? Well, that's going to be from 0 to 3 pi over 4, which is over here. But r is negative. So that's actually going to graph on the opposite side down here. So that's going to be the corresponding. It's 0. So it goes from 0 to big to 0. So same thing. It goes from 0 to big back to 0. Now I'm not going to do the rest, but there's a bunch of ways we can get this answer. And let me show you. If you look at this red region, if I take 1, 2, 3, 4, 5, 6, 7, 8 of those, that will give me the area. So I can do that. I can do the integral of 1/2 or 8 integrals of 1/2. Let me erase that. Of 1/2, 0 to pi over 4, because this is 0 to pi over 4. So that's why I go 0 pi over 4. I do 8 of them because it takes 8 of these little pieces to make the whole thing. And the area is 1/2 r squared. R would be 2 cos 2 theta squared d theta. And now it's just a matter of working that out. You pop that in your calculator to get your answer. Or, check this out. Can't I just take 4 of these to get the area? So I could technically do 4, 1/2, and that's produced from pi over 4 to 3 pi over 4 to get that loop. So I can go from pi over 4 to 3 pi over 4, and I would do my r squared, 2 cosine 2 theta squared d theta. You can pop both those in the calculator. They should give you the same answer. And there's many more ways you can do that, but we'll stop at that. For this next example, we have a circle with a radius 1 right here. And we have a cardioid. If you're to graph this, it's a cardioid because it's kind of like a sideways heart. So they call it a cardioid. And I didn't write down all the info. We want the area of the region that's inside, don't know how to spell, that's inside the circle and outside the cardioid. So if you look, I've had it shaded. Inside the circle is green, and outside the cardioid is going to be the pink. And the region that has both will be this one. So it's this shaded region, if you can see. So how do I find that? So the way I'm going to do it, I am going to find the area of the circle from the starting angle here to the ending angle here. So from that angle to that angle, I'm going to sweep out the blue area. But that's too much stuff there, right? So I have to subtract the cardioid. So I got to subtract this stuff here. So I'm going to set this up, but I'm not actually going to calculate this. So the area of the blue is going to be 1/2 r squared, which is 1 squared d theta. And that angle to that angle appears to be from pi over 2 to 3 pi over 2. And if we look at the red cardioid, it starts at 2 and an angle of 0. That's out here. As I sweep, at pi, it's going to get to 0. So as I sweep this way, the radius gets smaller, smaller, smaller till 0 at pi. And after pi, it starts to increase, bigger, 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 and at the end, it ends up at 2 again. And that's what's going on here. So what angle is that point where r is 1? We could figure it out analytically, or it's quite obvious pi over 2. If we look at this graph, it equals 1 at pi over 2 and 3 pi over 2. So it looks pretty clear that this red area here is gotten by starting at this angle and sweeping all the way through to 3 pi over 2. You get these red pieces here. So you have to be able to see that. So I will subtract 1/2, again, starting at pi over 2, ending at 3 pi over 2 of r squared, which is 1 plus cos theta d theta. You can pop that in your handy-dandy pocket calculator, and that will get you the area of the region inside the circle and outside the cardioid. Okay. You can try this on your own for fun if you wish. Find the area in the first quadrant between the graphs of 3 cosine x and r equals 1 plus cosine x. Well, 3 cosine x is the blue one, and the black one is, no, I got that backwards. Let me think. So the blue one is 3 cos x, and the black one is 1 plus cos x. And so between those two graphs in the first quadrant, so first quadrant, we've got to be in between those two. And between the graphs, my interpretation between the graphs is going to be that region, right? So how am I going to do that? Well, I'm going to sweep out that area from here to here. So I'm going to find this whole area, this whole thing, which is going to be 1/2, the integral from 0. I don't know where I'm going to end, but it's going to be 3 cos x squared d theta. So that's the area of that piece. Now the question, where do these intersect? Well, that's why we graph them both on the xy coordinate, and we find that. If this was your graphing calculator, you'd find the intersection of the two graphs, and it's pi over 3. So this will be pi over 3. And then you need to subtract all this extra stuff in here. All this is extra. I only want that area. So that I'm going to mark with green. So we are going to sweep that area out. So I need to subtract 1/2, and it's also 0 to pi over 3 as we look at that. And it's going to be r squared. This time it's going to be 1 plus cos x squared d theta. Pop those in your calculator, and you get your answer. And that's example 6. All right, next topic, arc length of a polar curve. Well, we found the arc length of parametric equations. In fact, the formula for parametric equations look like that. Well, here's the good news. We can change a polar, an r, into an x and a y, which is parametric. So we do that. You find the derivative of x using product rule, the derivative of y using product rule, and you pop that in here and here, and you integrate it, and that's how you can get length of a polar curve, quite simply. So we already know how to do that. We just convert the polar into parametric. So there is your formula. Now, I'm going to show you this. Now, you can memorize this simplified formula, but I'm going to find dx dt squared. So I'm going to square this. So that's going to get f squared sine squared plus 2 f of theta, f prime of theta. Well, it's going to be minus. And then I'm going to get sine theta cosine theta. And then plus f prime of theta squared cosine squared theta. That's going to be dx d theta squared. Now I'm going to find dy d theta squared. dy d theta squared. That's going to be f squared of theta cosine squared theta plus 2 f of theta, f prime of theta, sine theta, cosine theta, plus f prime theta squared, sine squared theta. Now, if we add these together, as this one suggests, those are opposites. They're going to cancel out. And then we end up with this, dx dt, or d theta squared, plus dy d theta squared, equals, so I have this. I'm going to factor out the f squared. So f of theta squared, it's going to leave me with a sine squared plus cosine squared. And then on this one, I'm going to factor out the f prime of theta squared. And that's going to leave me with cosine squared plus sine squared. And the beauty, this is 1, this is 1. And I end up with f of theta squared plus f prime of theta squared. Wow. So if you convert this to parametric form, then you square them each, and then you combine, you end up with this. So that's what this is here. This is the simplified arc length formula for polar. You can memorize that, or just convert to parametric and use your parametric equation. So either way is bueno for me. I am going to use a shortcut because I don't want to do all that work. So what's the arc length? A to B. Oh, okay. This is interesting. We need to figure out what creates this whole thing, 1 plus cosine theta. And did I graph it below? I didn't. I'm going to have to do this. I'm sad. Okay, so plug in 0. At 0, you're going to get 2. You're going to start out here. Well, to get to 0, this has to be negative 1, and that's going to happen at, my brain's not working, at pi. So to me, when you get to the angle pi, this is finally going to reach 0. And so it's going to slowly decrease, get to 0. So that's at pi. And then if I put in numbers bigger than pi, So this will be negative, but as I move from here this way, it becomes a smaller negative, because out here it's -1. Then it's like less than -1. Here's going to be 0. So at this point, we're going to reach 1. Our r is going to be 1. So we're going to be at a point 1. So what's going to happen? We're going to subtract less and less negative. It's going to come out to here. And then when will it get back here? That's going to occur when it's 2. Well, I'll get 2 when this is 2 pi. So concluding from that, 0 to 2 pi is what I need to get the full shape. So to get the arc length of this whole shape, I'm 0 to 2 pi. And the formula is going to be the function squared, 1 plus cosine theta squared plus, and then it's going to be the derivative squared. Well, I can find that. R prime is minus sine theta. So it's minus sine theta squared d theta. So that you would just pop in your calculator to get your answer. That is example 7. Okay, I'm doing 2 of these. Okay, I don't know if I'm doing all parts. I don't know what I'm doing because, again, long video. Let S be the region bounded by the graph of the polar curve. Okay, so this is a graph of that from 0 to radical pi. Find the area of S. Okay, I'm not going to do the math part. I'm just going to set it up. So it's 1/2. I start at 0. I end at radical pi. R squared. So it's going to be 3 radical theta sine theta squared d theta. So pop that into your calculator and you'll have an answer for that. You know what? I'll give you the answer because I have them right here. I have them. This is the 2019 test. So you can look this up. It's 2019. Oh, I didn't. Okay, I lied. I thought I had the answers, but I can pop them up real quickly here. I'll get those. This is number 2. I'll get the answers to 2. Okay. So that comes out to be, if you work this out, about 3.534. That's the area of S, if you were to do that. Okay, the average distance from the origin to the point on the polar curve. So we want the average distance, but what is the distance from the origin to any point? That distance is r. So they want the average of r. So how do you find the average of anything? You integrate the function. I'm just going to put r. I'm not going to write it all out again. You integrate from beginning to end, and then you divide by the width. So that's the formula for the average of any function that you learned last year. If you pop that in your calculator, you get 1.579 or 1.580, depending if you truncate or round off. That's the average distance, which is just the average r. Part C, there's a line through the origin with a positive slope m that divides the region S into 2 regions with equal areas. So let me do that. So there is some line that's going to divide it into equal areas. Okay, let me read that. Write but do not solve an equation involving one or more integrals whose solutions gives the value of m. Okay, the slope of this is m. Okay, if that's the slope, how do you find the angle? Well, here's where you have to think a little bit. The slope is rise over run, right? So the slope technically is tangent, because tangent is opposite over adjacent. Let me write it this way, y over x. Tangent is y over x. The slope is y over x. So we have to arctan. Arctan of m gives you your angle. So that's your theta. So if we want that, let's see, write Bedouin-Self equation involving one or more integrals whose solution gives the value of m. So we want to integrate from 0, and we want to stop at this angle theta, which is arctan m. So we're going to go to arctan m, and the area of that region is 1/2 r squared d theta. That's going to give me the area of this region. Well, that should be half of our first answer. So we set that equal to 1/2 of our first answer of 3.534 blah blah blah. We probably should write the whole thing out. So that is the answer. Or you just copy all of this and put it here. And that should be your answer. Okay, so that's part C. Part D, let k greater than 0, for k greater than 0, a sub k be the area of the portion of the region S that is inside the circle, r equals k cosine theta. Find the limit as k approaches infinity of a sub k. So we're going to have a circle. Okay, let's see. Let me erase this and find out what's going on so I can picture this. Calculator time. If I were to graph that circle on a calculator, we did one earlier, r equals k cos theta. We did one of those here. No, we didn't. We did one over, I thought we did. Maybe we didn't. Let me double check. I thought we did. Yeah, right here. R equals 3 cos theta. Basically, it tells you where you start. And you get a circle that touches the origin. Okay? Now, you could have graphed this on your calculator and got a pattern of this. But on this problem, that's going to get us a circle right here. So let me draw that in. And I want to make that no fill. Well, let me get a line there. No fill. Ooh, can I empty that? I don't think I can. There we go. That's better. So that's going to be the function r equals k cos theta, where this right here is k, the distance out there. Okay, the area be the portion that is inside the circle. A sub k be the area of the portion of region S that is inside the circle. So basically, I've got this figured out. They want this region here. Okay, so to get that, wow, okay, here's what we have to do. This is pretty crazy. We have to sweep out the region. I'll do it here. And let me move this circle over. That's better. So to get the first region, we have to go from there to that angle, wherever that is. And then after that, we got to add all that orange part. So it's a pink part and an orange part. So up here, let's do the pink part. It's the integral from 0, because we know this starts at 0, and it stops where they intersect. So I got to find where they intersect. And then it's 1/2 r squared, which is that function, what is it, k cosine theta, r squared d theta. But then I have to add the yellow part. The yellow part is going to start at some question mark. I don't know what that angle is. I keep going till I get to here, which is pi over 2. Because the cosine pi over 2 is 0, so that's going to be that. So we're going to end at pi over 2, but I need to know where those points are. And my r for that is going to be my r of theta. I'm not going to write all that in, squared, d theta. So that's going to be my formula, but let's see if I can find where these intersect. Where does k cos theta equal the other function that we have, 3 radical theta sine theta squared? So that's the point. If I could find that theta, which I am not sure how I'm going to do, that would give me that area. All right, I'm going to cheat. Let me make sure that I did this correctly. Okay, we want the limit as k goes to infinity. Okay, this makes sense. As k goes to infinity, here's the logic. Eventually, we're going to get this huge circle, right? And what it's going to end up being is the area of this region here. Because as the circle gets bigger, it's going to be pretty much flat there. So it's going to end up being, I don't know if you can see that. I did all that work, but it's not necessary. Because we're getting a circle, the ginormous circle that's going to be like this. It's just this area, stopping at pi over 2. Wow, that was a tough one, because you had to kind of analyze it. The way I was going was leading into a bad path. So the limit as k goes to infinity of that is just going to be 0 to pi over 2 of our r of theta squared d theta. So I can ignore all this too. So what just happened again? Logically, as this circle gets bigger and bigger and bigger, eventually it's going to come straight down. It's so big. And so when it comes straight down, the region that we're finding the area is going to be from here all the way to 90 degrees. So to find that area, it's going to be from 0 to 90 to get that region of S. So that's why I go from 0 to pi over 2, which is 90, 1/2 r squared d theta. And you just pop that in your handy dandy pocket calculator, and you get 3.324. So that one was a tough one. I don't know if I didn't cheat and look at it, what I would have done with that. All right, last example. What year is this? Let me try to remember. I have it saved here. This is 2009 Form B. 2009 Form B. So part A, this is number 4, so this is non-calculator. 2009 Form B, no calc on this. So write an expression for the area of S. Well, that's easy, right? 1/2 r squared d theta. But what angles forms this? So that's going to be mapped out. Let me zoom in a little bit. I'll do blue. So it's going to be mapped out by some starting angle and ending angle. But what angle is that point right there? And you might say pi, and you would be wrong. So let me show you why. I want to know when r either equals 1 or possibly -1, right? Because I can get to this point either by going 1 or pointing that direction and going -1. So let me see which one works. I'm going to subtract 1 from both sides. -2 cos theta equals 0. Cos theta equals 0. Well, theta must be pi over 2. So it looks like pi over 2, r would be 1, but that would be that point, right? Pi over 2, 1. So that's not it. So let's subtract 1 from both sides. We're going to get -2 cos theta minus 2. Divide both sides by -2. Cos theta equals 1. Inverse cosine theta equals 0, because the cosine of 0 is 1. Okay, so when you plug in 0, your r is -1. So when your angle's 0, there's your first point. That angle is 0 radians. Crazy, right? That's 0. So you're going to start at 0. Where are you going to end? Well, I'm going to end when I reach 0. My r is 0. So now I want to set my r equal to 0. So 0 equals 1 minus 2 cos theta. I'm going to get 1 equals 2 cos theta. Divide both sides by 2. Cos theta is a half. When is cos theta a half? That's going to be pi over 3. So believe it or not, craziness, this angle here is going to be pi over 3. And this angle here, that's going to be 0. So I'm going from 0 to pi over 3. There is the answer for part A. Kind of crazy, eh? And that's the area of S. Area of S is that. B. Well, we want dx d theta and dy d theta. So we have a formula. X is r cos theta. And y is r sine theta. So they want dx d theta and dy d theta. So I just take the derivative using product rule. Leave the first alone. Take the derivative of the second. Plus, take the derivative of the first, which will be 2 sine theta, and leave the second alone. So I get that. And then I find dy d theta. I leave the first alone, and I take the derivative of the second. I take the derivative of the first, and I leave the second alone. And there are my dx dt's and my dy dt's. Now these will simplify a bit. So let me do some simplification. So when I multiply these two, I'm going to get positive 2 cosine sine. And there's 2 cosine sine. So that's going to be 4 cosine sine. And then that times that gets me minus sine theta. So that would be dx dt simplified, dy or d theta. Now dy d theta, let's see what happens. This will get me minus 2 cosine squared. Oh, interesting. I'll just rewrite this. I think it'll make my life easier. That's going to be cosine theta. Then when I distribute this, that's going to be minus 2 cosine squared theta plus 2 sine squared theta. If I factor the 2 out, or minus 2, I'm going to get cosine squared theta minus sine squared theta. And that's, I'm going to leave it like that. I could rearrange that, but I think we're good with that. I could do some double angle stuff or other things, but I think we'll just leave it like that. We're good. So that's dy d theta, dx d theta for part B. Part C, write an equation in terms of x and y for the line tangent to the graph of the polar curve at the point where theta is pi over 2. So we want equation in terms of y and x for the line tangent where theta is pi over 2. So we need the x and y coordinate and the slope. Well, the x and y theta at theta is pi over 2, we need dx d theta at theta is pi over 2. We need dy d theta at theta is pi over 2. This will help us get the slope of the tangent line. Then we have to find the x and y coordinate, which we can do. All right, so if we plug in pi over 2 into the dx d theta, cosine of pi over, I don't want to do that. Cosine of pi over 2 is 0. That's gone. Sine of pi over 2 is 1, so it's negative 1. And then plug in pi over 2. Cosine pi over 2 is 0. Cosine pi over 2 is 0. Those are gone. Sine of pi over 2 is 1. So negative 2 times negative 1 will be positive 2. So dy dx is dy d theta over dx d theta, which is going to be 2 over negative 1, which is negative 2. All of these should have it theta is pi over 2. Theta is pi over 2. Theta is pi over 2. So now we have the slope is negative 2. Now we need the x and y coordinate of those points. Well, let's see what we have. So we need to use this to plug in pi over 2 to see what happens. So we got to get x at pi over 2 and y at pi over 2. I think I can do that. Put pi over 2 here. That's 0. That x is just going to be 0. That's pretty easy. I can do that. Then plug in pi over 2 for y. Sine of pi over 2 is 1, so that's just 1. That's going to be 0, so I'm just going to get 1 for y. And I get y minus y1 equals m, x minus x1, y minus, that's 1, not 0, or not y. Y minus 1 equals negative 2, x minus 0. There is my equation of my tangent line. I am done with this